Welcome to this solution walkthrough. Today, we'll be tackling LeetCode problem number 822, card flipping game. This problem challenges us to identify the smallest number that can appear on either side of a card, provided it meets specific conditions. We'll explore how to approach this problem step by step and break down the logic to find an efficient solution. Let's get started. In this problem, we are given two arrays, fronts and backs, each of length n. These arrays represent a collection of cards, where the ith card has a number written on its front side, which is fronts, I, and another number written on its back side, which is backs, I. The key is that you can flip any card, effectively swapping the numbers on its front and back sides. Your goal is to find the smallest number that satisfies two conditions. First, the number must appear on at least one side of some card, either the front or the back. Second, the same number cannot appear on both sides of any single card. If no such number exists, you should return 0. This setup introduces an interesting challenge of evaluating the cards to determine the smallest valid number while adhering to these constraints. The output for this problem is a single integer, which represents the smallest number that meets the conditions we just discussed. If no such number exists, the output should be 0. Let's understand this better with some examples. In the first example, the array's fronts and backs are given as 1, 2, 4, 4, 7, and 1, 3, 4, 1, 3, respectively. The output is 2. This means that after analyzing the cards, 2 is the smallest number that meets the conditions. We'll soon explore why this is the case with a detailed explanation. Here's the explanation for the first example. The number 2 appears only on the front of the second card, so it satisfies both conditions. On the other hand, the number 4 is invalid because it appears on both sides of the third card. Similarly, the number 1 is invalid as it appears on both sides of the first and fourth cards. The number 3 is also invalid because it appears on both sides of the fifth card. Lastly, while the number 7 is valid, it is larger than 2. Since we are looking for the smallest valid number, the answer is 2. This example highlights how you must carefully evaluate each number's occurrence to determine its validity. Let's look at another example where fronts and backs are both 1. Here, the only number is 1, but it appears on both sides of the single card. As a result, there is no valid number that satisfies the conditions, and the output is 0. This demonstrates that when all numbers on a card appear on both sides, no selection is possible, and we must return 0. In the final example, fronts is 1, 2, 3, and backs is 3, 2, 1. The output in this case is 1. Here's why: the number 1 appears on the front of the first card and the back of the third card, but it does not appear on both sides of any single card. This makes it valid. Similarly, the numbers 2 and 3 are also valid as they appear on different sides of different cards but not on both sides of the same card. Among these valid numbers, the smallest is 1, so the output is 1. The problem also includes constraints to guide your solution. For instance, the lengths of fronts and backs are always equal, each number falls within the range of 1 to 2000, and the solution must handle up to 1000 cards efficiently. Additionally, certain edge cases, like all numbers appearing on both sides or having only one card, require careful consideration to ensure the solution is robust and accurate. To solve the card flipping game problem, we need to find the smallest number that appears on either side of a card, but which does not appear on both sides of the same card. A natural starting point is a brute force approach. Here, we consider every number that appears in the fronts and backs arrays as a potential candidate. For each candidate number, we verify whether it satisfies the condition of not appearing on both sides of a card. To implement this, we first gather all numbers from both arrays into a set of candidates. Then, for each candidate, we check whether it is valid by iterating through all the cards. Finally, we track the smallest valid candidate. While this approach is conceptually simple, its time complexity is inefficient. Constructing the candidate set requires O(n), and verifying each candidate involves checking all cards, which means O(n squared) time in total for large inputs. The brute force approach, while straightforward, has significant drawbacks. It is inefficient for larger inputs because it unnecessarily checks all possible numbers, even when some can be eliminated early. To address this inefficiency, we can use an optimized approach based on key observations about the problem. Specifically, we observe that any number that appears on both sides of the same card cannot be valid. With this insight, we can focus only on numbers that do not meet this condition. The optimized solution involves two main steps. First, we identify all numbers that appear on both sides of any card, these are the invalid numbers. Then, we scan the fronts and backs arrays to find the smallest number that is not in the invalid set. This allows us to eliminate unnecessary checks and drastically improve the efficiency of our solution. The optimized approach has a much better time complexity than brute force. Identifying the invalid numbers requires iterating through the cards once, which takes O(n). Checking the validity of all other numbers also takes O(n). As a result, the overall complexity of the optimized approach is O(n), making it much more scalable for larger datasets. Beyond its efficiency, this method also has the advantage of being simple to implement. By focusing only on numbers that matter and avoiding redundant comparisons, we achieve a solution that is both practical and elegant. This makes the optimized approach a significant improvement over the brute force method, especially for larger input sizes. The optimized approach is the clear choice for solving this problem due to its balance of simplicity and efficiency. The key insight that any number appearing on both sides of the same card is invalid allows us to prune unnecessary checks, ensuring a linear time solution. While the brute force method is easier to conceptualize, its O(n)² complexity makes it impractical for larger inputs. By contrast, the optimized approach requires slightly more initial thought but is significantly faster and scales well. This trade-off between simplicity and efficiency is well worth it, as the optimized solution leverages the problem's constraints to avoid redundant computations. In conclusion, the optimized approach is not only more efficient but also provides a cleaner and more scalable strategy for solving the card flipping game problem. In this problem, we are tasked with finding the smallest number that can appear on either the front or back of a card, provided that the number does not exist on both sides of any single card. To solve this, we will be working with two arrays, fronts and backs, which represent the numbers on the front and back of each card. The first step is to identify numbers that cannot be chosen. A number is invalid if it appears on both the front and back of the same card. To efficiently track these invalid numbers, we can use sset, which allows for quick lookups. By iterating through all the cards, any number where fronts I equals backs I is added to this invalid_set. Once we have identified these conflicting numbers, we can focus on finding valid candidates. A valid number must appear on at least one side of a card and must not belong to the invalid_set. We'll collect all such valid numbers, ensuring that we have a pool of candidates to work with for the final step. After gathering the valid candidates, the next step is to find the smallest valid number. Using Python's built-in min function, we can efficiently determine the smallest number from the list of valid candidates. If no valid numbers exist, either because all numbers are in the invalid_set or there are no cards at all, we return 0, as prescribed by the problem statement. Now, there are a few key insights to consider. First, the process of identifying conflicts early simplifies the problem significantly by reducing the pool of numbers we need to evaluate. Using set for storing conflicting numbers is particularly advantageous, as it provides constant time lookups. This ensures that our solution remains efficient even with a large number of cards. Additionally, handling edge cases like when all numbers conflict or when no cards are provided ensures the solution is robust. Finally, our approach uses optimal data structures, a set for conflicts and a list for valid candidates, to balance efficiency and clarity. Let's break the algorithm into detailed steps. First, we initialize our data structures. We create an empty set called invalid_set to store conflicting numbers and an empty list called valid_candidates to store numbers that can potentially be chosen. Next, we iterate over each card. For every card, if the number on the front matches the number on the back, we add that number to the invalid_set. This ensures that all conflicting numbers are identified early. Once we have our invalid_set, we proceed to collect valid candidates. For each number in the fronts and backs arrays, we check if the number is not in the invalid_set. If it is not, we add it to the valid_candidates list. Finally, we determine the smallest valid number. If the valid underscore candidates list is not empty, we return the smallest number using min. If the list is empty, we return 0, indicating there are no valid numbers. To analyze the complexity of our approach, let's start with time complexity. First, iterating over the cards to populate the invalid underscore set takes n, where n is the number of cards. Collecting valid candidates involves processing both the fronts and backs arrays, which results in 2n, or simply n. Finding the smallest number in the valid underscore candidates list takes k, where k is the number of valid candidates. Combining these, the overall time complexity is n plus k. For space complexity, storing the invalid underscore set requires n in the worst case, as all numbers could conflict. Similarly, storing the valid underscore candidates list also requires n. Therefore, the total space complexity is n. This balance of time and space efficiency ensures that the algorithm works well even for larger inputs. To understand the algorithm in action, let's walk through an example. Suppose we have fronts equals 1, 2, 4, 4, and backs equals 4, 3, 4, 1. In the first step, we identify conflicts. For the first card, the front is 1 and the back is 4, so there's no conflict. For the second card, the front is 2 and the back is 3, again no conflict. For the third card, the front and back are both 4, so we add 4 to the invalid underscore set. For the fourth card, the front is 4 and the back is 1, which is not a conflict. At the end of this step, the invalid underscore set contains 4. Next, we collect valid candidates. From fronts and backs, we exclude 4 and find the valid numbers are 1, 2, and 3. Finally, we determine the smallest valid number. The valid underscore candidates list is 1, 2, 3, and the smallest number is 1. Based on the example, the output for the given input is 1. This demonstrates how the algorithm efficiently identifies and eliminates conflicting numbers, then determines the smallest valid candidate. Let's also consider some edge cases. If all numbers conflict, such as in the input fronts equals 1, 1, and backs equals 1, 1, the invalid underscore set would contain 1, and there would be no valid candidates, so the output would be 0. Similarly, if there are no cards provided, as in fronts equals and backs equals, the output would also be 0 because no valid numbers exist. The algorithm is optimized to handle these scenarios by leveraging the invalid underscore set to eliminate conflicts early, ensuring that we don't waste time rechecking numbers later. Additionally, its linear time complexity relative to input size makes it suitable for large datasets, while the use of efficient data structures ensures clarity and performance. The provided code solves the card flipping game problem efficiently. The main goal is to find the smallest number that can appear on the front or back of a card such that it is not present on both sides of the same card. Step-by-step explanation. 1. First, the code initializes an empty set same. This set will store numbers that appear on both the front and back of any single card. The input fronts and backs represent the numbers on the front and back sides of the cards respectively. Each pair, F, B, corresponds to a single card. 2. Using a for loop, the code iterates through the paired values from fronts and backs using zip. If the front number F equals the back number before any card, it adds this number to the same set. This step ensures that all numbers that are invalid, i.e., appear on both sides of the same card, are tracked. 3. Next, the code initializes the result variable to float, INF, representing a very large value. This will track the smallest valid number found during the subsequent steps. 4. The code then iterates over all numbers in the combined list of fronts and backs. For each number, it checks if the number is not in the same set, i.e., it is valid. If valid, it updates the result to the smaller of the current result and this number. This step ensures that the smallest valid number is identified. 5. Finally, the code returns the result if it is not equal to float, INF. If result remains float, INF, it means no valid number exists, so the code returns 0. Complexity analysis. Time complexity *. The code iterates over the cards once to populate the same set, n, and again over the combined list to find the smallest valid number, 2n. Thus, the total time complexity is n. space complexity asterisk the same set consumes k space, where k is the number of unique numbers that appear on both sides of a card. Here, we start by importing the necessary libraries and defining our solution class along with the flip game method. The goal of this method is to determine the smallest number that can appear on the front of a card after flipping, while ensuring it does not appear on both sides of the same card. First, we create a hash set called same to store numbers that appear on both the front and back of the same card. We then iterate through the array's fronts and backs to populate this set. If a number is the same on both sides of a card, we add it to the same set. Next, we initialize a variable result to integer.max_value, which acts as an infinite placeholder for our smallest number. This ensures that as we evaluate potential candidates, we can easily update result with smaller values. Then, we iterate through all numbers in the fronts array. If a number is not in the same set, it becomes a candidate for the result, and we update result to the smaller value between itself and the current number. After checking the fronts array, we repeat the same process for the backs array. For each number in backs, if it is not in the same set, we again update result to be the smaller value between itself and the current number. This ensures we consider all valid candidates for the smallest possible number that can be on the front of a card after flipping. Finally, we check if result is still equal to integer.max_value, which would mean no valid number was found. In this case, we return 0. Otherwise, we return the value of result as the smallest valid number. This approach efficiently filters out invalid numbers and ensures we get the correct result by leveraging the hash set in two simple loops. To solve this problem, we start by identifying numbers that appear on both sides of the same card. Looking at the input arrays, the first card has the number 1 on both the front and the back, so we add 1 to the same set. The second card has different numbers on each side, so we move on. For the third card, both the front and back have the number 4, so we add 4 to the same set. Finally, the fourth card has different numbers again, so no addition is made. At the end of this step, our same set contains 1, 4. Next, we look for the smallest number that is not in this same set. To do this, we combine all numbers from both the fronts and backs arrays into a single list. As we check each number, we skip 1 because it is in the same set, but when we encounter 2, we note that it is not in the set, making it a potential result. We continue checking and skip 4, but we also find 3, which is not in the same set. However, since 2 is smaller than 3, our result remains 2. Thus, the smallest valid number is 2, and the output is 2. Now let's consider a case where all numbers are invalid. In this input, every card has the same number, 1, on both its front and back. As we iterate over the cards, we see that 1 is repeated on both sides for all 3 cards, so we add 1 to the same set each time. After checking all the cards, our same set contains only the number 1. Next, we try to find the smallest number that is not in this set. Combining all the numbers from fronts and backs into one list, we see that every number is 1. Since 1 is in the same set, we skip over it entirely, leaving no valid number to choose from. Because we cannot find any number outside of the same set, the result remains undefined, which we treat as 0 in this problem. Thus, the output is 0, indicating no valid number exists. Here we analyze a more complex example with mixed valid and invalid numbers. Starting with the input, we check each card to identify numbers that appear on both sides. The first card has different numbers, so we move on. The second card also has different numbers, so no addition is made. On the third card, both sides show the number 8, so we add 8 to the same set. The fourth card again has different numbers, so no further additions occur. At the end of this step, our same set contains 8. Next, we search for the smallest number not in the same set. Combining all numbers from fronts and backs into one list, we sequentially check each number. The first number, 3, is not in the same set, so we update our result to 3. We continue checking and find 7, but since 3 is smaller than 7, we skip it. We also skip 8 since it is in the same set. Finally, we find 9, but again, 3 remains the smallest valid number. Therefore, the output for this example is 3. To analyze the time complexity of the solution, we start by examining how the same set is built. Here, a single for loop processes all the cards by iterating through the fronts and backs lists simultaneously with the zip function. Since there are n cards, this iteration takes n time. For each card, we check if the front and back numbers are equal, which is a constant time operation, O1. Adding an element to a set is also O1 on average, so the entire process of building the same set is O(n). Next, we look at the iteration over all numbers in the combined fronts plus backs list. Creating this concatenated list involves taking two lists of size n and combining them, which takes O(n). The resulting list has 2n elements, and iterating through it requires O(2n), which simplifies to O(n). Each number is checked against the same set in O1 time, and updating the result is also O1. Therefore, the total time complexity for this part is O(n). Finally, the return statement at the end involves a simple comparison, which is O1, and does not affect the overall complexity. Now, combining all the steps, we add together the time complexities, O(n) for building the same set, O(n) for processing the concatenated list, and O1 for the return statement. This gives us an overall time complexity of O(n). Next, let's analyze the space complexity. The first contributor to space usage is the same set, which stores numbers appearing on both sides of the same card. In the worst case, all n cards could have the same number on both sides, meaning the same set would contain up to n unique elements, requiring O(n) space. The second contributor is the concatenated list fronts plus backs. This new list contains 2n elements, so it also requires O(2n), which simplifies to O(n) space. Finally, there are a few additional variables such as result and loop iterators, but these only use constant space, O1. Adding these up, the total space complexity is O(n) for the same set, O(n) for the concatenated list, and O1 for other variables, resulting in an overall space complexity of O(n). Let's now explore how this algorithm performs in different scenarios. In the best case, all numbers in fronts and backs are unique, and none of them belong to the same set. Even in this scenario, the algorithm must iterate through all the cards and their values, so the time complexity remains O(n). In the average case, some cards have the same number on both sides, but the operations in complexity remain consistent, as the algorithm handles these cases efficiently using the same set. The time and space complexity here are still O(n). In the worst case, every card has the same number on both sides, leading to the largest possible same set containing all n numbers. Even with this, the linear nature of the operations ensures that the time complexity remains O(n), and the space complexity also stays O(n). Comparing this to a naive approach, a brute force solution would check every pair of cards to determine valid numbers, leading to O(n)² time complexity. The optimized solution we're analyzing avoids this inefficiency by directly iterating over the combined list and using a set to track invalid numbers, reducing the time complexity to O(n). Finally, let's provide a mathematical justification for the big O analysis. The operations involving the same set, such as insertions and membership checks, are O1 on average due to the efficient hash table implementation of sets. Iterating over the fronts and backs lists takes O(n) time, and concatenating these lists also requires O(n). The dominant term in the algorithm is the linear iteration over all values in the combined list, making the overall time complexity O(n). Similarly, the space complexity is dominated by the memory allocated for the same set and the concatenated list. The same set requires O(n) space in the worst case, and the concatenated list, which contains 2n elements, also requires O(n) space. Additional variables like result and loop iterators use constant space, O1, which does not affect the overall scaling. Therefore, the total space complexity is O(n), confirming that the algorithm is both time and space efficient for this problem. Now let's discuss some common mistakes that could trip you up in this problem. First, failing to properly handle duplicates is a frequent error. If a number appears on both sides of the same card, it cannot be a valid candidate. Ignoring this condition violates the problem's constraints and will lead to incorrect outputs. Next, there's the issue of inefficiency. Using brute force to test all possible numbers on all cards can result in a time complexity of O(n)², which becomes impractical for larger inputs. Instead, using sets to efficiently exclude invalid numbers allows you to solve the problem in O(n). Another mistake is assuming that the input arrays are sorted. There's no guarantee about the order of numbers in the cards, so relying on sorting may lead to incorrect assumptions and eventual failure. Keeping these points in mind will help you avoid common pitfalls and build a solution that satisfies the problem requirements. Continuing with the common mistakes, misunderstanding the output is another frequent issue. The problem specifically asks for the smallest valid number, so returning a number that doesn't meet this condition is incorrect. This can happen if the constraints aren't carefully implemented. Additionally, overcomplicating the logic is something to avoid. Solutions that involve unnecessary checks or multiple nested loops not only make the code harder to read but also increase the chance of bugs creeping in. Overcomplicated logic makes it easier to miss edge cases and typically results in inefficiencies. By focusing on clarity and simplicity, you can build a robust solution that is less prone to errors. Now let's look at some valuable insights, especially in the context of interviews. The key pattern to recognize is that this problem revolves around identifying numbers that appear exclusively on one side of all cards. Using sets to represent numbers on the front and back of the cards allows you to quickly identify and exclude invalid numbers. From an optimization perspective, instead of iterating over all possible numbers, you can narrow the search space to just the numbers present on the cards. This drastically improves efficiency. It's also important to consider edge cases, such as when all numbers are duplicates, when there are no valid numbers, or when there's only one card. Being prepared to discuss these scenarios demonstrates a deep understanding of the problem. Finally, under the given constraints, where the number of cards is capped at 2000, efficient solutions with a time complexity of O(n) or O(n) log n are feasible, whereas brute force approaches would be too slow. Related problems like LeetCode 349, 961, 448, and 287 also touch on themes like set operations, finding duplicates, and identifying missing elements, making them great practice for this kind of problem. Lastly, let's explore some alternative approaches to solving this problem. One effective method is set-based filtering. Here, you maintain two sets, one for invalid numbers that appear on both sides of a card, and another for potential candidates. By iterating through the cards, you can populate these sets and identify the smallest valid number efficiently in O(n). The trade-off is that this approach requires additional memory for the sets. Another option is a direct array check, where you manually iterate through all numbers on the cards to determine their validity. This method is simpler to implement but less efficient, with a time complexity of O(n squared). A third alternative involves sorting. By sorting the numbers and then checking their validity in sorted order, you can simplify the logic. However, sorting adds overhead with a time complexity of O(n log n). While these approaches have their pros and cons, understanding them allows you to choose the one that best fits the constraints and requirements of the problem. Thank you for watching. We've covered the key aspects of solving LeetCode problem number 822, from understanding the requirements to implementing an efficient solution. Remember, practicing these types of problems helps strengthen your problem-solving skills and prepares you for coding interviews. Be sure to like and subscribe for more coding tutorials and tips. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!